All right, so in the last video, we ended with a proof of the monotone convergence theorem, which remember says that a monotone sequence, that is a sequence which is increasing or decreasing, converges if and only if it's bounded. So the main theoretical significance of this is that it tells you that a certain kind of sequence converges without having to know what the limit is ahead of time. Okay, so it says you only have to check that it's bounded in order to know that it converges. So we saw the proof is that the sequence, in this case, if you have a bounded monotone sequence, it has to converge to either the supremum or the infimum of the elements of the set of elements of the sequence. But in practice, that infimum or supremum might not be computable. Okay, so that really is only if it's sort of only a theoretical proof. I mean, so you sort of know what the limit is theoretically, but you don't, in any practical sense, you won't in any practical sense be able to compute what the limit is. Okay, so, but you often will be able to tell that a sequence is bounded. It's much easier to say this monotone sequence is bounded than to exhibit the limit explicitly. Okay, so that's the kind of idea, and the monotone convergence theorem it points to more general theorems that we'll develop, especially the Cauchy criterion, which will tell us how to figure out whether a sequence is convergent without knowing the limit, and that would be a general sequence. So where we're aiming is to remove this monotone condition, because most sequences aren't monotone. Okay, and as I was saying in the last lecture, series give a pretty, a series with positive terms give a sort of standard application of the monotone convergence theorem. So an example here, sort of one of the main examples of this monotone convergence theorem would be to show that the sequence of partial sums of the series of 1 over n squared, that those partial sums are bounded, and therefore this is a convergent series. So is convergent. And there's a couple ways to prove this, I would say. So if we're looking at a partial sum here, Sm is the sum from n equals 1 to m of 1 over n squared. What we can do is we can sort of bound each of the individual terms, so sort of replace each of the individual terms with something a little bit larger, such that we know that the series you get when you do that change is convergent. So this is what I have in mind here. So this 1 over n squared, each of the 1 over n squared, well, n is, well, the simple thing you can say is, so you're just going to focus on 1 over n. So 1 over n squared, 1 over n squared is 1 over n times n, and I'm going to replace one of these n's with something, and n is bigger than n minus 1, right? So when I invert them, I'm going to get that n is less than, 1 over n is less than 1 over n minus 1. And so I can use that here. The only problem is when n is equal to 1. When n is equal to 1, this n minus 1 in the denominator doesn't make sense. So I can say this is less than, let's just say less than or equal. I'll peel off the first 1 here, and I have the sum from n equals 2 to m of 1 over n times n minus 1. And then just a silly little relabeling. So if I shift all of these down by 1, then I can shift the n up by 1. So this is a 1 plus sum from n equals 1 to m minus 1, and 1 over n plus 1 times n. You see, I'm shifting the labels down by 1, and so therefore I have to shift the labeling of the variable up to compensate for that. Okay, so these are both just saying the same thing. And let me erase that. And we saw last time, right, that this sum, we actually figured out what this partial sum is explicitly. This was just, so this is just equal to 1 plus, so you have this one, and then this thing was 1 minus 1 over this thing plus 1. So this is just going to be 1 plus 1 minus 1 over m, or 2 minus 1 over m. Okay, and in any case, that's less than 2. So, and this is independent of m, right? So that means for any m here, the mth partial sum is less than 2. So this is using a series we looked at last time, right? We computed the partial sums of this series here explicitly just by induction. Okay, so making use of that here, we bound the partial sums by 2, and so therefore this series is convergent by the monotone convergence theorem. Okay, so this implies that this series converges by the monotone convergence theorem. All we had to do is see that all of the partial sums, of course, the SMs, they're bigger than 0, right? Okay, so in absolute value, all of the SMs would be bounded by 2. So converges by the monotone convergence theorem. Right, I mean, I guess I should say explicitly, you know, we have that SM is less than or equal to SM plus 1 for all m, right? Because the difference between the mth partial sum and the m plus first is, right, to get the m plus first, so this is just in general, the m plus first partial sum of a series is just the mth partial sum of the series plus the m plus 1 term of the sequence, right, that you're actually summing up. Okay, so this just says sum up the first m plus 1 terms. Of course, that's the same as sum up the first m terms plus the m plus 1th term. And so since all of our terms here are greater than 0, say greater than 0, greater than or equal to 0, this is going to be greater than or equal to Sm. In fact, we could say strictly greater than in this case. Okay, right, so we know our sequence is monotone, it's bounded by this computation, and so we have a bounded monotone sequence of partial sums, and therefore we must have convergence by the monotone convergence theorem. So this is kind of proof 1. There's another proof which uses a more geometric series kind of idea. So proof 2 is basically this. So if we think about, so you have 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36 plus 1/49 plus 1/64 plus, and so a partial sum is going to look like this. We have to stop somewhere. So the idea is kind of to group these together. So if we look at these two here, right, we have 2 terms, and the second term here, the 1/3 squared, is less than the 1/2 squared, right? So this is less than 2 times 1/4. Right, because 1/9 is less than 1/4. And if I take these terms here, then each of the subsequent terms is less than this one, right? So we can say this is less than 4 times 1/16. Okay, so of course that's 1/4. This is 1/2. And we can continue in this fashion. So we would go out. So this is, so here where we started, we had 1/2 squared, and then 1/4 squared, 1/8 squared. It looks like we're doing all of the powers of 2, so we're going out to where the n is a power of 2. So what we would have here, this is 1/8 2 to the third squared, right? And then what we would go out to is 1 over 2 to the fourth squared. And we would we'd collect all of those terms. So that this collection, there would be 8 of them. So 8 times 1 over 64, and that would be 1/8. And what you can see here is that when you add these up, 1 plus a half plus a fourth plus an eighth, that's a geometric series. So this partial sum here, or let me say it this way, let's say we're looking at this partial sum that just goes out to this first grouping with 1 term, this second grouping with 2, this third grouping with 4. That is the partial sum. So we have, let's see, this is 2 to the third here, so that's the 8th term. This is the 7th. It's 1 before, so you're going to have in general sort of a 2 to the k minus 1. Right, you're going to go out just before the 2 to the kth term and cut it off. So what you can do is you can group these up. So this partial sum, which goes up to 2k minus 1, you can take them in groups starting with each of the 2 to the i's. So you're going to have 1 over n squared, so you're just summing 1 over n squared, but you're going to start with, let's see, so you're going to start with n equals, so each of one of these little groupings here, it starts on a 2 to the I, say. So this is going to be 2 to the I, and then it goes up to 2 to the I plus 1, the next power of 2, but minus 1. And that starts with I equals 0, right? Because that corresponds, 2 to the 0 is 1, so that corresponds to n equals 1. So we start with I equals 0, and then that goes up to I equals k minus 1. Right, so when I equals k minus 1, we have 2 to the k minus 1, as we should. So this goes up to k minus 1. Okay, so this just breaks up the sum of this partial sum into these various groups. And in each one of these groups, the 1 over n squared, the 1 over n squared, the n squareds are getting bigger as you go to successive terms, right? So each of these 1 over n squareds, they're smaller than the first one in the grouping, right? So this is going to be less than, we have a sum, let me just say less than or equal to be safe. So in each of these little groupings, you can replace the n squared with just 2 to the I squared. Okay, so instead of letting n go throughout this whole range, right, each of those successive n's are bigger, so this denominator gets bigger, so this fraction gets smaller. So each of those later terms is smaller than the very first one in the grouping, which is the 2 to the I term. Okay. And then, well, like up here, right, and then, I mean, this is just a constant. So like in here it was 1/4 and we had 2 terms. Here it was 1/16, right, that's just the starting term. We had 4 terms. So in general, we just have 1 over 2 to the I squared, and we have however many terms are in this sum here. Right, and however many terms are in this sum, it's the difference between the number up here and down here. So we're starting at 2 to the I, we're going up to 2 to the I plus 1 minus 1. And the number of terms that we have there are the difference between this and this plus 1. Okay, so like the number, you just think, if you had, it was a sum from 1 to 5, right, there's clearly 5 terms there. That's 5 minus 1 plus 1. Okay, so this then becomes, this is the sum from I equals 0 to k minus 1 of, we have the difference between those two plus 1. So that's 2 to the I plus 1 minus 2 to the I over 2 to the I squared. And this top one, we just factor out a 2 to the I. That's going to cancel with the one on the bottom. I equals 0 to k minus 1 of then we'll just have 2 minus 1 is 1 over 2 to the I. Right, and this is just a geometric series, or it's a partial sum of a geometric series, and the sum is 1 minus 1 over 2 to the k. Right, we're going up to k minus 1, so that's your, if you remember your formula for the sum of the sum of x to the i's from 0 to m. Right, you always get m is the power here is m plus 1. Okay, so and then this is divided by 1 minus 1/2, which is just 1/2. Okay, so this is less than 2. Right, so all of these partial sums for all of the 2 to the k minus 1 partial sums are less than 2. So that bounds these particular kinds of partial sums, right? But a general partial sum is not 1 less than a power of 2, but it's not hard to handle that. So for a general partial sum, Sm, you can just, you just take a k big enough so that 2 to the k minus 1 is bigger than m. So in particular, you can just take, so Sm is going to be less than or equal to S sub 2 to the m minus 1. So in fact, this isn't hard to establish by induction. M and 2m minus 1. M is always less than or equal to 2m minus 1. And I think it's always strictly less than whenever m is bigger than 1. So that holds, and then that is less than 2. All right, so this is for any m. All right, so that puts a bound on the partial sums by doing this grouping argument and using the facts we know about these geometric progressions here. Okay, so that's two different arguments. The second one a little bit more involved, but it actually leads into an idea that we'll be looking at a little bit more with a slightly different series in a second. This idea of grouping terms like that. Okay, so then just to sort of finish the argument, this implies that that the Sm converges. So the sequence of partial sums converge by the monotone convergence theorem. All right, so a little bit of work, maybe a little bit of cleverness to put a bound on these partial sums, but it is a lot easier than figuring out, what the actual limit of the partial sums is itself. That was a major open problem back in the 1700s that Euler solved and made him instantly famous. Okay, so this is the utility of the monotone convergence theorem. Okay, so a related series, so example, and this is the example of the harmonic series. So we have the series of 1 over n's. So this is probably the simplest type of series that you would think might converge, because these 1 over n itself is of course going to 0. But this is a famous example of a series that actually is divergent. So note that 1 over n, so the an's, that sequence approaches 0, but the sum, the infinite sum, the infinite series, is divergent. Okay, so the terms we're adding together are getting smaller and smaller and smaller, vanishing, going to 0, but nonetheless, the infinite sum can still go to, right, be divergent, be unbounded. And so this is a monotone sequence. The sequence of partial sums is a monotone sequence. but it turns out to be not a bounded sequence. Okay, and this was proved by I'm not really entirely sure how to pronounce this, Oresme, in the 14th century. I think he was some kind of monk, and his work was basically forgotten for basically almost nobody knew about it at the time, and it was only rediscovered sort of hundreds of years later after other people had figured out that this harmonic series diverges also. And again, the idea is this grouping idea from above. So if we look at some partial sum, sort of a generic kind of partial sum, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. Let me maybe pause. Okay, so going out a little bit there. The basic idea is to try to show that this, that a partial sum like this, I don't know, let's say we stop here or somewhere after here, that this is bigger than something which is going to infinity, which is getting progressively larger and larger, which is unbounded. So the idea is this. So if we go look at some point in this sequence of terms, right, every term before it is bigger than it, right? So if we look at any term, if we look at the one before, we can sort of replace the one before. If we are willing to put a bigger than or equal sign, we can replace the one before with that one. So for example, here, these two, 1/3, this is bigger than 2 times 1/4. Right, because 1/3 is bigger than 1/4. And looking at 1/8 here, the 4 terms, including the 1/8 and the 3 before it, this is bigger than 4 times 1/8. And this grouping is bigger than 8 times 1/16. And notice these are all equal to 1/2. 1/2 equals 1/2. And so basically, clearly this can continue, right? If we go from 1/17 to 1/32, then that's going to be 16 things which are at least 1/32 in magnitude. And again, that's 1/2. So we just keep getting these big groupings, sort of exponential size, 2 to some power number of things, and then times 1/2 to that power plus 1. So those groupings each have a size at least 1/2. And since this goes on, indefinitely, right, then in general, this is going to be bigger than 1 plus some multiple of 1/2. So let's say if we look at a partial sum like, so the general pattern would be something like 1/2 to the k plus 1, right? That would be like this 9 here. And then out to plus ... plus 1/2 to the k plus 1. And this would be bigger than, so the 8 here, that's like this 8, that's like the 2 to the k. So it should be 2 to the k times 1/2 to the k plus 1. And so every term in here is bigger than except for 1/2 to the k plus 1 itself, is bigger than 1/2 to the k plus 1. And the number of terms is, you can just count it, it's this, right? So we're at the 2 to the k plus 1 term, and the number of terms is, so we're at the 2 to the k plus 1, we started at the 2 to the k plus 1, so subtract those two and add 1, and what you get is just, it's just 2 to the k, indeed. So what we find here is that we have what? We have 1, and then we have how many 1/2s? Well, let's see here. So we have 1/2 to the 1, 1/2 to the 2, right? That gives us the second half. 1/2 to the 3, that gives us our third 1/2. So for every one of these, so this is going to be, right, so this whole big sum here then is bigger than 1 plus 1/2 times k plus 1. And so if this is the this is the partial sum going all the way out to the 2 to the k plus 1. So the partial sum 2 to the k plus 1, that's equal to that. That's bigger than that. Yeah, I guess I don't know. So what you can just say generally is that s to the 2m is bigger than 1 plus 1/2 times m. Okay. Yeah, and I guess you got to say bigger than or equal to just for when m equals 0 for this to make sense. In any case, then this shows that that the sequence of partial sums is unbounded. Okay, so this implies that the partial sums of this infinite series are unbounded. For any possible potential bound capital M, right, I can always take little m bigger than that capital M, right? So sort of the sketch of the proof would be, given m greater than 0, you can choose m such that, right, you want this 1 plus 1 over 2 times m to be bigger than m, and so that means your little m should be bigger than 2 times big M minus 1. Right, so choose m such that m is bigger than 2 times big M minus 1, and then you can see that the mth 2 to the mth partial sum here, right, is going to be bigger than or equal to 1 plus 1/2 of this, and then that's just set up exactly to be bigger than this capital M. So for any potential bound on this sequence of partial sums, you can break it. Okay, so then, right, s to the 2m, that's bigger than or equal to 1 plus 1/2 times m, which we just saw, and m, this is bigger than 1 plus 1/2 times 2 times big M minus 1, and that is equal to 1 plus big M minus 1, which is equal to m. Okay, so that shows rigorously that your partial sums are unbounded. So this is sort of a parenthetical proof if you want to see the rigorous proof that that's unbounded. Okay, so that shows your harmonic series cannot converge, but the rate of divergence is very slow. So based on this estimate we did here, if you want to be confident that your partial sums are bigger, let's say bigger than or equal to 100, right? Then, well, yeah. So I mean, it would just be this, right? You need your m to be bigger than 2 times 100 minus 1. So 2 times 99, so 198. So you would need to go out to the 2 to the 198th partial sum, which is just enormously big. I mean, it probably passes 100 before that point because this is just an estimate. But in any case, you see that you get a sense of how slowly this thing is likely to be diverging. Okay. So now the next theorem that I want to go over is very interesting. Essentially, part of it's a theorem of Koshi, and it really showcases his particular genius, which is that he sort of sees these ideas that we've been looking at. So this grouping idea that we were doing with the 1 over n squared, right? So this grouping idea here is the same kind of grouping idea that we were doing here in this proof by Oresme from, this is like back in the medieval period. So Cauchy knows about this kind of idea and says, why don't we try to apply this idea to more general kind of series? Right, so basically what we have here in each of these cases is we have a series where the terms are decreasing as we go along, right? So the terms themselves are decreasing. So in other words, our sequence, the terms, the ANs, they're monotone. They're monotone decreasing. And so he wants to take a look in general at a series with terms like that and see what he can do with this grouping idea. Okay, so basically, don't let any good idea go to waste. See how far you can push it. And so that sort of general idea for generating some new mathematics, Koshi takes that and produces the following theorem. So this is called the Cauchy condensation test, and it occurs when you have a decreasing sequence of non-negative numbers. Okay, so this is like, right, so just like our 1 over n or 1 over n squared series above. And what Cauchy does is he looks at that grouping idea. So he takes that grouping idea and can show that if that the original series that you can make out of this sequence, right? So you take your sequence, you make a series, that series converges if and only if a related series converges. So the condensation is that this sequence here, you sort of condense it to a much sparser sequence, right? So you just take the A1, A2, A4, A8, A16, all the multiples, all the powers of 2, right? But then you include a multiplier, right? So this is coming from the grouping. The 2 is coming from a group of 2, and you're sort of replacing by the A2, and the 4 is coming from your grouping of 4, grouping of 8, grouping of 16, and so you're creating this new series with just the power of 2 A's, but then multiplied by powers of 2. And so your original series converges if and only if this other series converges. Okay, so it's being condensed down to this much sparser sort of subset of the A's. Whether that thing converges determines entirely whether your original series converges. Okay, so as I said, we'll look at the proof here. The proof is interesting because it's just a more or less straightforward kind of implementation of a generalization of Oresme's idea of grouping terms together like that to prove that the harmonic series diverges. So the basic idea is like this. You're going to, again, focus on the powers of 2 here. And what you're going to try to do is show that, right, if this partial sum here is related to a partial sum of this series here, and what you want to do is put an upper bound and a lower bound on it in terms of this other partial sums of this other series. So basically, if partial sums of this series are bounded, right, then that will imply a bound on this. So this partial sum here is going to be less than or equal to some partial sum here. And so if these are bounded, then these are bounded. But also that this partial sum is bigger than or equal to some multiple of a partial sum of this thing. So if these partial sums are unbounded, right, so if we can say that this partial sum is bigger than or equal to, something that we know is becoming unbounded, then this will also be unbounded, being bigger than it. So we sort of want we want an upper bound and a lower bound on this partial sum of our original series in terms of the partial sum of this sort of condensed series. And the idea for doing that is this. So let's see this. So if we look at like A4 here, we want a less than or equal. So I know if I go further into the series, so further terms out in the series, these are getting smaller, right? So I know like A5, I know that's less than or equal to A4, and I know A6 is less than or equal to A4. I know A7 is less than or equal to A4. And similarly, I know A3 is less than or equal to A2, etc. So I can say A1, that's less than or equal to A1. A2, let's see, so, whoops, sorry. plus, I know A3 is less than or equal to A2, so that's going to give me 2A2, right? And my these four terms here, A7, 6, 5, 4, that's less than or equal to 4 times A4. And then we'll have plus in the next round, let's see, A8 through A15, that's going to be, the sum of that's going to be less than or equal to 8 times A8, right? Plus 8 times A8, etc. Right, so we see that, and so if we go out to A15 here, that's less than that. Okay, so we'll know that if this, if partial sums of this series here are bounded by something, that's going to imply a bound there. And then we can do a sort of a similar idea, but to get a lower bound. So here, like we went forward, so A4, we went forward because as we went forward, these got less, and we could replace all of these with A4. And now I think we're going to go backwards. So to get this, to get something smaller, so looking at the A4, we know that A3 is bigger than or equal to A4, right? And A1 is bigger than or equal to A2. So let's see here. So A4 and A3, that's going to give us 2A4. Right, A4 is less than or equal to A3, so 2A4 is less than or equal to these two terms here. And then let's go further down here. So the next one, we'll go down to A8. We know that A7, A6, A5 are bigger than or equal to A8. So that's going to give us 4. So we're going to have plus 4A8. That's going to cover these terms here. And then we would have to go down to A16. So if we went down to A16, then we would have 8 times A16, right? And so it's sort of clear what the pattern is. So we have A2 here is bigger than or equal to A2, and then we just kind of have A1 hanging out there. What we can do is write this thing as, so this is going to be 1/2 A1 plus 1/2 of A1 plus 2A2 plus 4A4 plus 8A8 plus 16A16. Right, so we see that this partial sum here is bigger than or equal to some just finite term, and then a multiple of a partial sum of this. Okay, so that's the basic idea here. And there's, we sort of had to consider different partial sums. So this less than or equal to only works up to the A15 for the A15 term, and then and then for this type of the lower bound, we had to go out to A16. All right, so there's some just little details to keep track of, but basically that's the kind of idea. So let's try to write this down. So so the partial sum out to, we have a power of 2, so 2 to the k, but then minus 1. That was less than or equal to, we had the, so the power of 2 minus 1, this was 2 to the 4th, and then we went down to the previous power. So if we denote, so let's denote this, so this is a partial sum of this other series, right? We can denote the partial sums of that by t. So this is less than or equal to the partial sum of this other series out to, let's see, this was a k minus 1. Right, this is the going out to k equals 3 here to get the 8, right? So we had 2 to the 4th power here, and that 4 corresponded with a 2 to the 3rd power here. So we had to take that 4, reduce to 3. So we had that estimate there, and then we also had S sub 2 to the k as being bigger than or equal to, we had 1/2 a1 plus 1/2 1/2 of, so let's see, yeah, so that was so 2 to the k, so that k was equal to 4, and that was t sub 4. That was the fourth partial sum of the other series. Okay, so it looks like we had those kinds of estimates. So let's see if we can write the proof of this. Okay, bigger. Oh, that's the biggest eraser I have. Okay, so so we'll show that. So let's see, proof. So suppose that this series converges. Okay, so the outline is going to be, this thing converges. So if we denote its partial sums by this notation, these partial sums are bounded, and this partial sum is going to bound the partial sum of this partial sum of our original series. Okay, and so let's see. So suppose that this thing converges. Okay, so denote the partial sums by, let's say, so the sum of the a's, n equals 1 to m, that would be s sub m, and the sum from k equals 0 to m of 2 to the k, a sub 2 to the k, that's going to be t sub m. Okay, so here we have s1, s2, s3, etc. Here we have t0, t1, t2, t3, etc. Okay, so to show that that the partial sums, or to show that this series converges, so to show that the AN series converges by the monotone convergence theorem, we just need to show the S sub m are bounded. Okay, so now we're going to observe what we did before. So observe that, so S sub 2 to the k minus 1, this is going to be 1, or excuse me, not 1. It's going to be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5, a sub 6 plus a sub 7. And remember, we said we're going less than or equal to. So let's see. So each of the, so A7, A6, A5, those are all less than or equal to A4, right? So these are going to be our grouping. So our grouping is we go forward from the powers of 2. Okay, so you go forward from powers of 2 plus dot 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 plus we're going out to s to the 2k minus 1. So that means our grouping here, so last grouping is going to be starting at the 2 to the k minus 1 power, and then going out to a sub 2 to the k minus 1. Okay, so that's going to be our grouping there. And then what we have, I guess I have to get rid of this. Then what we have is that this is less than or equal to a1 plus 2a2 plus 4a4. plus plus. And then this is 2 to the k minus 1 times a sub 2 to the k minus 1. And that is just equal to the 2 to the k minus, or sorry, the k minus 1 partial sum of the condensed series. Okay, so we have that. And the point is, well, we know that that these t's are going to be less than, so that's going to be less than some m, right? So because these are this series here converges, so the partial sums are bounded, right? And we're just trying to say that this bound is going to work for the other series. Okay, so that's less than m for some m since. So that's some m bigger than 0 since the tm converges, that sequence converges. Okay, so we've bounded some of the partial sums, right, the ones of the form 2 to the k minus 1, but for any m, right, so you take any m, so now for any m, but now s sub m, that is less than or equal to s sub 2m minus 1. Right, 2m minus 1 is always bigger than or equal to m, and then that is less than m for any m in the natural numbers. So Sm is a bounded sequence bounded monotone sequence, hence convergent. Okay, so to complete the proof, we have to go the other way. So now suppose that our condensed series diverges. Okay, so we have a divergent sequence of partial sums, but the partial sums are monotone, so that must mean that the sequence is unbounded by the monotone convergence theorem. So since the partial sums are monotone, and that's using the non-negativity of the terms here. So the partial sums are monotone. This implies, and so the only way a monotone sequence can be divergent is if it is unbounded by the monotone convergence theorem. So this implies the partial sums, this implies they are monotone, or excuse me, unbounded by the monotone convergence theorem. Now what we're going to do is we will show that our original series diverges by showing it's unbounded. So we observe, so we're going to look at, we look at s sub 2 to the k. Right, this is like in our scratch work sort of before the proof, s sub 2 to the k. This is, so we have a1 plus a2 plus a3 plus a4 plus ... We go all the way out to a sub 2 to the k. So the last, so we have a sub 2 to the k minus 1. Then we have a sub 2 to the k minus 1 plus 1, and we go all the way out to a sub 2 to the k. Okay, so this is our last grouping here. And then we have prior groupings. And what we're doing is we're going backwards from powers of 2 now. So backwards from powers of 2, backwards from the power of 2, 2 squared, and then we have 2 to the first. Okay, and this is bigger than or equal to. All right, so we're just going to leave the A1 and the A2 alone. The A3, that's bigger than or equal to A4. So this is plus 2A4 plus, right, dot, dot, dot. And the last one would be, we have, let's see, 2 to the k minus 1 terms here. So we have a 2 to the k minus 2 to the k minus 1 number of terms, and that's 2 to the k minus 1 times 2 minus 1, which is just 2 to the k minus 1. So 2 to the k minus 1 times, so each of these terms here in the first part is bigger than or equal to the last term, right? Because this last term is the smallest. Our sequence is decreasing. So this is a sub 2 to the k. All right. And so this is, so if we, right, so this 2 is off by a factor of 2 from the 4, right? This is off by a factor of 2 from the 2 to the k. So in general, what we have is we have like a 1/2 of what we're sort of expecting here. So this is A1 plus 1/2 of 2A2 plus dot, 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 plus 2 to the k minus 1, A sub 2 to the k. And then what we can do is we can also peel off 1/2 of A1. So if we leave 1/2 of A1, and then we have plus just 1/2 of, and what we're going to have is t sub k. So the kth partial sum of t. Of the kth partial sum of the condensed series. Okay, so that's bigger than or equal to that. And A1 is bigger than or equal to 0, so to just simplify things, we can say this is bigger than or equal to 1/2 of tk. Okay, so this partial sum here is bounded above, or bounded below, excuse me, by half of this partial sum of the other series. But what that means is, right, since the partial sums of this series are unbounded, that means for any given possible bound, I can find find a tk bigger than it. All right, so I can make these tks as big as I want, which means I can make the s sub 2ks as big as I want. So that means that these elements, these partial sums are getting wildly big, and so that means that my original series is unbounded and therefore divergent. Okay, so given m bigger than 0, there is a k in the natural numbers such that t sub k is bigger than 2m. Okay, the 2 because I'm going to account for this factor of 1/2, right? So for any positive number, I can find one of these partial sums that's bigger than it, such that so thus s sub 2 to the k is bigger than or equal to 1/2 tk. That's bigger than 1/2 times 2m, so that's equal to m, right? So the s sub 2k there is bigger than that m bound, and that implies that that the partial sums of our original series are unbounded. So S sub m, that sequence is unbounded. And thus our original series diverges. Okay, so that completes the proof of the Cauchy condensation test. And really, it's just exploiting that nice little trick of Oresme from the medieval times, from the Dark Ages, basically, and trying to apply it to a more general situation. So that's really good. Good mathematics. Don't let any good ideas go to waste. Try to squeeze as much as you can out of them. So that's what Cauchy did there. Okay, so that's Cauchy's condensation test. Kind of just irresistible type of thing to look at when you're talking about the harmonic series. So that's a little bit of a detour, but a kind of fun detour in any case. And it has a nice corollary. So the corollary is that the series 1 over n to the p, so n equals 1 to infinity, this converges if and only if p is bigger than 1. So you might recognize this from calculus, from probably a Calculus II course, where you might have sort of justified this by comparison with an integral, with an infinite integral, which we're not going to do here, of course, because we're in analysis. We're all the way back in the roots of thinking about the real numbers. We're far away from having a rigorous theory of the integral, so that's not going to work here. But the Cauchy condensation test gives a nice proof of this. And just a little caveat here, this corollary is in the book, but the book doesn't say anything about what p is. And I'm going to take p to be a rational number here, because we have to know what n to the p means. Okay, and so just a little bit of a digression here. So if p is a rational number, we can write p as a over b, right, where a is an integer and b is a natural number. And this n is, of course, just a natural number, just a positive real number. So let's talk about, I guess, in general, if we have x, some positive real number, what it means to talk about x to the a over b. Well, so what this means is x to the, let's see, so it's x to the a, and then the bth root of that, or the bth root of x to the a. Okay, so it's not hard to show that that these things are both equal, and these are defined in terms of things that we've covered, right? So so if a is a positive integer, if a is a positive integer, that's just x times x times x, whatever a number of times. If a is a negative integer, then it's just the multiplicative inverse of x multiplied by itself, absolute value of a times. And then we talked about the existence of roots, right? So the second root, third root, fourth root. We rigorously proved that square roots exist, right? So the 1/2 root, and I discussed why the other positive, why the other natural number roots exist. Just a modification of the same proof shows that those roots work. So this power, rational power of x, makes sense. But from the perspective of thinking carefully about the foundations of the real numbers and what we know about how real numbers work, we should admit to ourselves that when we have just some real number y, right, or I guess I'll just say p. So p is just some arbitrary real number. What does x to the p mean? I mean, it's not entirely straightforward what that should mean. Like, what does x to the pi mean, or what is x to the square root of 2? What does that mean? So this can be developed in a number of ways. Probably the slickest way is to define the natural logarithm function or the exponential function and define things in terms of that. Or you can do this in terms of limits. So for a general real number, you can find a sequence of rational numbers approaching this, and then you can define this x to the p as x to those various rational numbers approaching p, and sort of as the limit of a sequence. That takes work to develop. Either approach takes work to develop. So really, we don't, don't entirely know what x to the p means for a general real number at the moment if we're building up things, mostly sort of from the ground up. So, I mean, this is true for more general real numbers, of course, but I'll just state the proof for rational numbers at the moment. So I just wanted to bring up this, sort of logical issue about raising real numbers to particular powers. That's not. It is a bit of a subtle issue. It's not immediate. Okay. So anyway, so here's the proof for the corollary. And it's pretty cool. The basic thing is that if we use the Cauchy condensation test, that we can turn this into a geometric series. And so basically, if we take only the n's that are powers of 2 to the k, then 2 to the k to the p is just 2 to the p to the k. And so then you have this geometric series where 2 to the p or 1 over 2 to the p is the ratio. So basically, what we have is, so by the Cauchy condensation test, so by the Cauchy condensation test, this thing converges if and only if let's see, so you replace the n with 2 to the k, and then you multiply by 2 to the k. And your sum is now from 0 to infinity. Okay, and so this is the same as our 2 to the k. So this 2 to the k up here, if we group that, that's going to be 2 to the k to the p minus 1. So this is 1 over 2 to the k to the p minus 1. And that's the same thing as 1 over 2 to the p minus 1 to the k. Okay, and this is a geometric series. So this is a geometric series. It converges if and only if the absolute value of 1 over 2 to the p minus 1 is less than 1. Okay, and this is always positive. So this is if and only if. So this happens exactly when exactly when 1 is less than 2 to the p minus 1. And so writing p as a over b, so a is an integer and b is a natural number. So we write p that way, and raising both sides to the b power, and raising both sides of the inequality to the bth power. We see this holds if and only if 1 is less than 2 to the a minus b. Okay, so now we just have an integer power of 2, and that's going to be bigger than 1 only when a minus b is bigger than 0. If and only if that, which happens if and only if a minus b is bigger than 0, i.e. a is bigger than b, i.e. going back to the definition of p, i.e. when p is bigger than 1. Okay, so that finishes that proof. Okay, so that's sort of should be a familiar looking fact from calculus, and a nice proof you probably hadn't been exposed to before using this Cauchy condensation test. Okay, so I think that's everything for this lecture. So it was a little bit more on the monotone convergence theorem, applying that to the series 1 over n squared. Then we looked at the harmonic series and saw that so that's an example of a monotone. The partial sums are a monotone sequence which diverges, and then we used the sort of generalized the idea of Oresme, Cauchy's idea, to generalize that idea to more general series, and then we had this this corollary of Cauchy's condensation test. Okay, so the next week in the lectures, we're going to go on to talking about the Boltzano Virustras theorem and the Koji criterion. So the Boltzano-Virustras theorem is really the key step in proving the Cauchy criterion, and the Cauchy criterion is what allows us to decide when a sequence converges without knowing what it converges to. Okay, so that is where we're going, and that brings us to the end of this lecture.